Okay. So let's remember what the question was. Um, if electron is considered as a point particle, then the energy stored in the electric field of the electron, the electric field produced by the electron has some energy in it. So what's that energy? Well, that energy has to be infinite for a point particle. So how can we resolve this difficulty? One way of resolving it is as thinking of it as it's a ball particle. So it's a particle with radius, some certain radius. In any case, in here I just used the model for a conducting shell. Electron doesn't have to be like that, but in any case, there's some kind of you can assume some kind of a charge distribution, in which case the formula will be quite similar to this. It will be of the same order of magnitude. But in any case, what appears is that well, this gives us some kind of a radius for the electron, but it doesn't solve the essential problem. And basically, in the experiments, we don't see any structure of the electron around this radius. Right? So I mean, at this length scale, the electron still looks like a point particle. The other resolution is this, right? I know that some of you will not like this. So let's say it like this. But this is something that we need to remember. In physics, all physically observable quantities depend only on the energy differences. So only energy differences are physical. Some people may also object to this, because we have defined things like the rest energy and things like that. But in any case, we can argue about these kind of things all we want. But in any case, if there's some kind of a change and there's a change in the energy, then the energy changes, the differences in the energy is the one that we should be concerned about, right? So as a result, I mean, if the energy is like infinite, it doesn't mean anything. So as long as I can do calculations with this and subtract an infinity from infinity, we can still have meaningful physics defined. So as a result, it's not a big problem that the energy of the field produced by an electron is infinite, right? I know that this is like a stupid way of resolving this thing, but let me think of it like this. So suppose we have like two electrons in here with the distance between them is, let's say, A, okay? So we would like to compute, for example, the energy of that. So to compute the energy of this one, so I'm going to label the electrons as 1 and 2, okay? So I'm just going to call U12 as the energy. So it's the energy of, yeah, that's the energy of E field produced by these two electrons, right? Let's just define it like this. In that case, this is also given as 1/1/2 of epsilon 0, the total electric field, basically, squared multiplied with the volume integral or whatever. So at the end, when you compute this integral, this gives you infinity. And the reason is that basically the difficulty, the divergence comes from places where, sorry about that, comes from places which are very close to the electron in here. I'm making all of these mistakes in here, right? So the electric field lines are pointing towards the electrons in that case. So the problem basically arises in these places near the electrons where the electric field is much stronger than we see at outside places. So the divergence comes from here. And so as a result, this divergence is still present, even if there are some other electric fields superimposed on that. That's not going to go away. And so as a result, this is still infinite. Now, what we do is, like, we can also compute the electric energy of electric field produced by the first electron alone. So let's say it like this. This is the energy of field let's say, produced by first electron only, let's say that the second is not present and the first one, we know that this is also infinite. We just computed this. And I can also do the second one too. So that's the energy of the field produced by the second electron only. And I know that this is also infinite. So I also know that this infinity is the same as this infinity. So these two infinities are equal to each other. But it appears that this infinity is different than that infinity. So if we are using the same symbol, but we cannot really understand the difference. So in any case, what I'm talking about is this difference in here. Okay, sorry about that. So presumably this is, for example, the energy of the electrons when they are too far apart, and that's the energy of the electrons when they are near. And when you compute that difference, this is like infinite minus infinite, infinite. It appears that you can still compute a finite result in here, in which case this is E squared divided by A, actually, which is the correct potential energy that we have computed for 2-point charges. Okay, so even though each of the electrons have infinite energy, and together they have infinite energy, you can still subtract infinity from infinities, and then you can still get a finite result. But you have to do some kind of a limit calculation in here. So I don't know how you would compute this. There are ways. It's not a difficult mathematical problem. It's not really difficult, actually. You can actually do this calculation. All you need to do is to write down this electric field as the dot product, basically, and then do the mathematical manipulation. So let me write it down like this. So that's the energy when electrons are far apart. Okay, and that's the energy when electrons are nearby. Okay, so we always compute the difference of two energies, and even when the energies are infinite, we can still make this calculation, do this calculation, and then compute a finite result. In any case, still, this is some kind of a resolution. It's not a perfect happy ending. I know that. Unfortunately, people meet similar kinds of infinities in the calculations when they are dealing with these point particles. This is actually the divergences that see in particle physics theory. They also resolve it somehow by using some other tricks and things like that. But at the end, they compute some quantities which are physically meaningful. So as a result, this is not magic. But of course, I mean, there are still some unanswered questions in here. Okay, so that's the only thing that I can say in here. I don't know if you have any questions about this, or if you have questions, perhaps you can ask me later. Okay, let me continue. All right, then I'm going to talk about this dielectric materials, dielectrics. There are a few things that we need to do. Again, there are some conceptual things in here. But we basically use some observation. Okay. What we have is this, we have a capacitor. Capacitor is a device that stores energy. And so let's say that C0 is the capacitance when the space between the place is empty. So this is the capacitance when space between plates is empty. So some people just call this as vacuum, actually. So capacitance when there's vacuum between the plates. So what we do is we don't change the geometry. We just fill the space between the plates with some material. And I think I'm going to use the red color for that purpose. So, so let's say it like this. So this is an insulator, but we are going to call this as a dielectric material. But any insulator would do. A conductor would not do, because conductor would basically just carry the charge on one plate to the other one. You can never fill that capacitor in that case. You can never charge that capacitor in any case. So C is the capacitance when space is filled with a dielectric material. Okay, so the observation is that we always have C is equal to K times, first of all, the capacitance increases by this procedure. It always increases. Moreover, the new capacitance can be expressed as some constant multiplied with the capacitance when there's vacuum. So let me use C0 in here, right? Where K depends only on material. And not on the geometry, and not on the geometry of the capacitor. All right, I think I didn't do this. So first of all, I should have explained this correctly. So capacitance always increases with the insertion of dielectric. So that's the first thing. It always increases. It never decreases. Moreover, it always increases with the same ratio, where that ratio depends only on the material. So in any case, C over C0, that's equal to K, depends only on the material. Okay, so K is apparently greater than 1 because capacitance always increases, where we call K as the dielectric constant. Of the dielectric material. Okay. So every material has a dielectric constant. You can think of it like that. For conductors too, I can associate a dielectric constant to them. But I mean, to understand this picture, you have to keep the conductors out of the picture. So as a result, whenever we talk about the dielectric material, they are always insulators, right? So that's the first thing. This is also the formula for, I mean, one way of using the dielectric constant in a formula, you just use this picture. So when you insert the whole space between the plates of a capacitor, somehow you can find a new capacitance by just multiplying the old capacitance with the dielectric constant. Okay. So that's one way, but there are other ways of using it. So let's say it like this. So find the E field between the plates when a dielectric is inserted. So I'm going to use this picture, parallel plate capacitor case, because since this capacitor is the simplest, we just use it a lot, right? So suppose that I have a vacuum filled, there's vacuum in here, a capacitor like that, And we then fill the space between the plates with a dielectric material. So I'm just going to show it. First of all, I'm going to draw this better. All right, whatever. Assume that these are straight lines. And then we have this dielectric material in here, right? And so therefore the capacitance somehow is increased. So I'm going to look at a situation where I have a charge Q on the plate, on positive plate, and minus Q on the other one. So this thing doesn't change. Let's suppose. Okay. So let's say that the electric field in that case is equal to E0. And what's the electric field in that case? Okay, let's do the electric field calculation. Here I know what to do, right? I mean, I'm just going to do the calculation in here, but at the end, we are going to see that we are going to see what we have in here. So first of all, I know that the electric field is equal to the potential difference multiplied with D, right? Because if there's a potential difference in here, well, the potential difference is basic. Sorry about this, extremely sorry. Potential difference is the integral of the electric field. So therefore, the electric field is potential difference divided by D. Again, I'm sorry about this. What's the potential difference? I then write this thing down in terms of the charge. This is charge divided by the capacitance value, right? So therefore, what is this? It's the charge divided by, well, the capacitance has actually increased, so therefore this is K times the capacitance in here. And so therefore I have a formula like that. So that's the charge divided by the dielectric constant multiplied with epsilon 0, area divided by D. Okay. So apparently the plate separation somehow cancels. And so as a result, I get like Q divided by the dielectric constant times epsilon 0 times A. Now I notice that there's a charge divided by area in here. That's the surface charge density, basically. And so as a result, the electric field would be sigma divided by K times epsilon 0. Right, that's basically what I wanted to say. Sorry about this. So if the surface charge density is sigma, what is the electric field in terms of sigma? That's the question that I was asking for. If there is no dielectric in here, the electric field is given by sigma divided by epsilon 0. But if there is a dielectric, then the electric field is given by sigma divided by K times epsilon 0. Okay. So what? So in that case, it appears that this dielectric constant is multiplied with epsilon 0. So it appears that in all formulas, right, formulas, K always appears next to an expression that contains epsilon 0. So for example, capacitance value. Capacitance is the dielectric constant multiplied with the capacitance due to when there's vacuum. But let's remember that the value that we have computed for the capacitance is epsilon 0 times area of the place divided by the separation. Again, we have the dielectric constant is basically appearing next to epsilon 0. Okay. So because of that, we have a new definition. So we just call that product, it is K times epsilon 0, as the permittivity of the dielectric material. Okay. So epsilon 0 is the permittivity of vacuum. You can still ask the question of what is permittivity? We have no physical explanation for it. So, I mean, apparently the name somehow implies that this material permits something, but what does it permit? What's the meaning of that? We still don't have any idea. So this is a concept that has a name. That's the only thing that you should keep in mind. So otherwise, trying to interpret it in terms of some physical terms might actually confuse you. So as a result, don't get confused by this, all right? So in any case, epsilon 0 is just a constant of nature. Whatever, it's just a constant that we have defined. But we are going to define a parallel quantity, a permittivity for each material. It is related with to the permittivity of the vacuum by the same relationship. It's the dielectric constant multiplied with the permittivity. So in any case, so as a result, the permittivity of all materials is always bigger than the permittivity of the vacuum. So somehow every material has a larger permittivity, not better, has a larger permittivity than the vacuum. Okay. But the idea in here is that if there is some dielectric material in a medium, I can still use the same formulas, but with epsilon 0 replaced by epsilon. So you can think of it like this. So let's say it like this. All formulas we have seen up to now are still valid. Are still valid. But now all epsilon 0 variables should be replaced with epsilon. Okay. So I'm not going to justify this. I cannot justify. It's just basically by just looking at these equations, I just postulate that this is the case, right? So I'm just going to claim that some of the results that we have deduced before would still be valid, but I just need to replace everything with every epsilon 0 with epsilon, right? So for example, I have some kind of a dielectric material. So that's a dielectric material, right? The red ones are always dielectric materials. And I have a single point charge inside the dielectric material, right? So that's a single point charge. Point charge inside a dielectric material. Okay, sorry about this. I need to drink some coffee. I need to get some energy. Let's say it like this. This is the electric field. I'm interested in the electric field. Field produced by a single point charge inside the dielectric material, right? So this also produces an electric field inside. And I can write down the formula. If I have a point in here, which is, if I have a point in here, which is at a distance little r from the charge, then the electric field in here is 1/4 pi epsilon q divided by r squared, right? I can still write down the same formula. So it's energy is, or the radial component, electric field is 1/4 pi epsilon charge divided by r squared. All I need was to replace the epsilon 0 with epsilon. That's it. So as a result, taking the dielectric material into account is actually very simple. Sorry about this. There's a R unit vector in here, or you can say that this is the radial component. What else? Let's see. What's the force between two electrons inside inside a insulating medium, for example? So again, this is dielectric. So I have an electron in here, minus E, and the electron here, another minus E. I know that these apply some repulsive forces to each other. So let me call this as F. And let's say that that distance is, I don't know, let's call it as R. In that case, the force has this magnitude. That's 1 over 4 pi epsilon E squared divided by R squared. So in any case, so as a result, I mean, the formulas can be easily modified. No problem with this. There's going to be a problem in here, but in any case, so let's just remember that this epsilon is 1 over k multiplied with epsilon 0. So as a result, you can see that the force applied by these two charges inside a medium is always smaller than the force that they would apply if they were inside vacuum. Okay? Or think of it like this in terms of the electric field. So a single charge produces an electric field inside a medium, but that electric field is again 1 over the dielectric constant multiplied with something else. So as a result, this electric field is again weaker than the electric field that they would produce inside vacuum. So as a result, what the dielectric material does is to weaken the electric field. It basically, it doesn't make it stronger. It makes the electric field weaker, okay? And it appears that all the insulators behave like that. We don't have any material that makes the electric field stronger. We don't have any material where the dielectric constant is less than 1. That's basically what I'm saying. So as a result, let me go back to this. I mean, some people try to understand this permittivity expression as saying that this is how the medium permits the electric field pass through. But it appears that the function of the permittivity is just opposite. So larger the permittivity, the material medium strongly eliminates the electric field, right? So in a way, the vacuum is the best medium for the strongest electric field. Inside dielectric materials, the electric field is much more weaker, right? That's basically, I mean, the actual use of the quantity is kind of gives an impression of opposite to the name, right? It's not the permittivity, perhaps it's the forbiddivity or something like that, or I don't know. But I mean, some people called it as permittivity about 100 years ago, or 200, I don't know. So as a result, this is why we keep using the same term, even though we cannot give a real physical, we cannot give a meaning that we can easily understand. Okay, there's a problem in here. Problem. What if we have two different media with different dielectric constants? Okay. Yeah, I was going to talk about the Gauss law. Sorry about this. But for the Coulomb's law too, we have a similar kind of situation. So I don't know. Let's say that we have water in here where the dielectric constant is about 80. And there's air in here where the dielectric constant is about 1. The dielectric constant of air is very close to vacuum. In any case, it doesn't matter whether this is water or air. It actually doesn't matter much. So suppose that I have a charge in here, charge Q. What's the electric field in here? Is it the, I mean, if I want to use the formula that I have written this thing, written down above, which electric field, which dielectric constant should I use in here? Which permittivity should I use? Should I use the permittivity of air or permittivity of water? Or for example, what happens if the point in question is like near the boundary in here? So you can see that there's some kind of an ambiguity in here. And in reality, the electric field produced is actually much more complicated than this. Let me try to explain it like this. If you draw the electric field lines, this one will be simpler. But what you observe is that the electric field lines is actually curved in water. They are not straight lines anymore. And then they somehow have this kind of a behavior, right? And we have these kind of electric field lines inside water. So as a result, the problem in here, if there are actually more than one medium with different dielectric constants appear, everything becomes complicated. So as a result, this is not valid anymore. Unfortunately, no. The electric field is not proportional to the inverse distance squared. That's not the case anymore. So you're going to actually learn how to solve this if you are in the master's program. You can actually find the electric field produced by charges in these kind of media, but it's actually a tricky problem. So as a result, it's no use to discuss these kind of problems in here. What's important here is that the electric field is too complicated now. Just keep this in mind, all right? So that's not a simple problem. I don't know if they actually curve down like that, but I think, yeah, I'm not sure about this thing, but this is definitely curved in water. I think it is still straight lines in air, but they don't actually originate. All of these lines do not originate from this charge, but they originate from another point. So in any case, it's too complicated for us. So as a result, just forget about it. Okay, I think I need to do this. So I have given this example. So all formulas that we have seen up to now are still valid, all right? But now all epsilon zero variables should be replaced with epsilon. So we have seen the Coulomb's law as an example for that. Let's see the Gauss law. Gauss law says that the electric field integral over a closed surface area is equal to the enclosed charge divided by epsilon zero. Right? Let me again show it like that. Right? If I have a dielectric medium in here with dielectric constant, so that's dielectric. If I have a single dielectric medium with a single dielectric constant, all I need to do is to replace this with epsilon, which is k times epsilon zero. That's okay. So let's say it like this, all right? I'm just going to write this thing down. So electric field dot with area, that's equal to the enclosed charge divided by epsilon is valid if whole space, the whole space is filled with the same dielectric. What happened to K? It's still in there. So the dielectric constant of the medium is basically the permittivity of the medium is dielectric constant of the medium multiplied with epsilon zero. So all I need to do is to replace this epsilon zero with epsilon, that's it. But only if the whole space is filled with the same dielectric material. So basically everything. So by using this, you can deduce the Coulomb's law. You can deduce the parallel plate electric field, sigma divided by epsilon, and things like that. So no problem with this. So that's okay. But if the dielectric, right? So let me actually show the surface something like that. All right. So that's my Gaussian surface. So let's call it as Gaussian surface. And just remember that I'm evaluating the integral of the electric field over that surface. So as long as the whole part of the Gaussian surface is inside the same dielectric, this is actually true. I'm just going to talk about this in a moment. But now let's talk about the situation in here where the space is filled with many dielectric materials, but with different dielectric constants. So here, let's say the dielectric constant is K1, here it is K2. This is water, this is air again, right? So therefore, this epsilon 2 and epsilon 1, they are different from each other. So epsilon 1 and epsilon 2 are different from each other. So we just choose a Gaussian surface. Let's say that I choose a Gaussian surface in such a way that part of the surface is one medium and the part of the surface in the other medium. So if I then write down the Gauss law, which is basically the integral of the electric field outside on the surface is equal to the enclosed charge divided by epsilon. But which epsilon is this? Is it epsilon 1 or is it epsilon 2? Right? Or epsilon 2. There's an ambiguity in here. Right? You can easily see that there's an ambiguity because, I mean, the Gaussian surface is not entirely within, I don't know, within this dielectric, for example. If it were, then I would definitely use epsilon 1, no problem with this. But here, part of it is in some other medium and the part of it is in some other medium. Okay? So since this is not a point, we're not talking about an electric field at a point in here. It's the electric field at different points. And so when we are talking about different points, some of these points might be inside a material with a different dielectric constant, in which case I cannot easily use this kind of an equation in here if the dielectric constant appears on the right-hand side. And that's the problem in here. So as a result, this is problematic. So as a result, just forget about it. But what happens is that if I move the dielectric to inside the integral, in that case, I can give a meaning to, I can give a well-defined meaning to this. Okay, so what I'm doing is like, here the dielectric constant is not a constant. It's a variable. It just changes from point to point in space. Here we have just one situation in here. So sorry about this. I'm saying dielectric constant, but basically permittivity that I have been talking about, all right? So permittivity is not a constant anymore. It has a value, some value in here. It has a different value on at different points. So as a result, it shouldn't appear outside the integral. It should appear inside the integral. Okay. So as a result, with this correction, the Gauss law is still valid, right? That's what I'm going to say. Unfortunately, I have to show some examples of using the Gauss law in that form. How should we use it? Because since the permittivity is changing with position, there might be some problems where this epsilon might have different values inside the integral. So as a result, I have to show you some examples of these kind of things. Well, I have some examples, so I'm going to show them to you in some offline videos, all right? So that's the Gauss law. Sorry, that's the Gauss law when different dielectric materials are present. Okay. So as a result, I mean, the generalization of this formula is tricky, but once you do this trick, that's okay. In all other formulas, all you need to do is to replace the epsilon zero with epsilon. Right? So in the Gauss law, we just need to evaluate, take the epsilon inside the integral. That's the only detail in here. So as a result, let's say it like this: calculation with dielectrics. I can give you these two rules. So the rule number one says that the capacitance value, if I fill it with the dielectric, if I fill all the space inside the capacitor with a dielectric, then the capacitance value increases by that dielectric constant. So that's the first rule. The second rule is basically, it tells you that you have to replace every permittivity of vacuum with permittivity of the dielectric material. Okay, and then you will be able to handle all of the problems with the dielectrics. Okay, so I'm going to solve a number of problems involving these and involving capacitor circuits. So there will be lots of problems in here. But there's still one thing that's left to explain: why a dielectric material somehow makes the electric field weaker. I need to also explain this in a different video, right? Just keep this in mind. So there's some explanation inside the book, but don't even read about it, right? So I think this is the last section, because this is very confusing. People usually confuse the mathematical tricks with the physical, what happens physically. So as a result, just keep this in mind. Okay, so let's leave it in here.